Yeah. Hello, Aruna here.
Hi, am I audible to you?
Not so clear. Can you try to improve it?
Is it better now?
Yeah, yeah. Now it is better.
Okay, thank you. So, can we start the presentation or you want to?
Just we'll wait and see how many have joined
Sure,
participants. Yeah, only 14 are there. Just we will wait 2 to 3 minutes.
no issues. Yeah,
Okay, okay. So you are student of Dr. Sopanpati.
that's correct. Yes.
Okay, okay. Actually, we were contemporaries at IS. He was my senior there.
Oh, very nice, very nice.
Yeah.
So, you are working where, madam?
Yeah, I work at National Aerospace Laboratories, CSAR lab at Bangalore.
Okay. Nice.
Just we'll wait another 2 minutes and then start.
Sure, no issues.
ಹೆಂಗೆ ಬೈ ಕೇಳಿ ಮೀಟಿಂಗ್ ಟೈಮ್
Okay, good evening, everyone. I'm Aruna speaking from the Electrochemical Society of India. I welcome you all for this sixth ECSI webinar, which is jointly organized by the Electrochemical Society of India and ECS IITM Student Chapter and Advanced Center for Energy Storage and Conversion Group at IITM. Today, we have Dr. Shivaramakrishna Chaitanya Sharma, who will be speaking to us today on computing a few electrochemical properties that can help us to identify whether a 2D material can be a promising anode material or not. I would like to introduce Dr. Chaitanya. Uh, Chaitanya Sharma is an assistant professor in the chemistry department at IITM, and his expertise lies in the fields of computational chemistry and material science. He is one of the developers of the quasi-diabatic PLDM scheme, and he implemented various non-adiabatic dynamics methods such as NFES, fused switches, surface hopping, QD-PLDM, and MMST in the DFTB plus package. During his PhD and postdoctoral research career, he excelled in the areas of non-adiabatic dynamics, low-dimensional materials, bioinorganic chemistry, organic photovoltaics, plasma-assisted catalysis, energy storage materials, and various other interdisciplinary research themes. Prior to his appointment, he did his postdoctoral research in the USA with Professor Brian Wong, Department of Chemical Engineering, University of California, Riverside, and with Professor Feng-Fei Huo, Department of Chemistry, University of Rochester, New York. Earlier, he earned his MS and his PhD degrees from the Chemistry and Physics of Materials Unit, Jawaharlal Nehru Center for Advanced Scientific Research, that is JNCSR, Bangalore, India, under the supervision of Professor Sopan Kepati. For a brief period, he had also worked with Professor S. Balasubramaniam at JNCSR. Now I request Dr. Shivaramakrishna Chaitanya Sharma to deliver the lecture.
Thank you very much, madam.
And meanwhile, if the participants have any questions, please put it in the chat box. We will take it up in the end. So, Dr. Chaitanya, please.
Yeah, thank you very much, madam. Thanks for the kind introduction. I will share my screen.
Can you be little louder? Again, the voice is little feeble.
Okay, madam. Is this better, madam?
Yeah, it is better now. Yeah, yeah.
You're able to see the entire screen, madam?
Yeah, we are able to see it.
Okay, thank you. Thank you very much, madam, for the kind introduction. Good evening, everybody. I'm assuming that most of you are students, but if there are any professors are also, welcome to the seminar. And first of all, I would like to thank Raman for giving.
You are not audible now. You are not audible. Dr. Chaitanya, you are not audible. Dr. Chaitanya, you are not audible.
Whether a specific 2D material can be promising anode material or not. Obviously, all of you will be knowing that any of the batteries will have an anode material and cathode material, and we are worried only about the anode material at this place. And specifically, we are trying to see whether a 2D material like a graphene, borophene, many kinds of 2D materials are there available right now. For the specific properties, for the specific ion battery, whether it's a lithium ion battery, sodium ion battery, etc. For a specific ion battery, whether a particular 2D material will be useful or not is what we are going to understand by computing a few electrochemical properties. What are these properties? How do we compute, etc. is what will be the subject of today's talk. Before going further, I would like to thank my mentors. As Dr. Aruna mentioned, I worked with Professor Sopan Kepati during my PhD at JNCSR, and I have worked majorly on the low-dimensional systems there, and also we studied various kinds of size, defects, etc. for these low-dimensional materials. After that, I moved to Professor Pengfi Huo at University of Rochester. There, I have developed a few non-adiabatic dynamics methods, and I have implemented a few in the DFTB plus package and used them to study organic photovoltaic devices, specifically to understand the charge transfer between these donor and acceptor materials. And after that, I have moved to Professor Brian Wong at the University of California, Riverside. There, I have used this ab initio molecular dynamics as well as the electronic structure methods to study various catalytical and environmentally important reactions. So, electrochemistry is somewhat new to us, but I will try to present whatever we understand about it, majorly from the electronic structure viewpoint. Okay. So, the first question that we need to ask is, why are we studying these energy storage devices? To answer that question, we all should be understanding that we should not be relying on the non-renewable energy resources, and we wanted to use the renewable energy resources. So, if this is not clear to us earlier, the recent Russia-Ukraine war has clearly shown us that if we are only relying on the renewable energy resources like petrol or diesel or any of these things, although the war is happening somewhere in the Russia and Ukraine, which is far away from India, we will have a clear impact here. So if our dependence on the renewable energy resources is more, non-renewable energy resources is more, then we will have impacts just by having some incident somewhere happening around far away from us. And this is also seen, for example, in the Europe and other countries where they try to put sanctions on Russia and so on and so forth. So why all this is happening is only because majority of the globe was relying majorly on the non-renewable energy resources, which is petrol and diesel. Of course, these reserves are not there available equally on a global scale. That means like when you see America versus India, like we all do not have the same amount of petrol that is reserved with us. So to go away from this dependency, one needs to go towards the renewable energy resources. And of course, it is not a new thing just because of Russia-Ukraine war. People are known about this one, and we have been continuously improving or trying to use more and more renewable energy resources, as can be seen from this particular graph. The amount of usage of renewable energy resources is increasing, and it has to be further increased. However, what is the problem with the renewable energy resources is they produce the energy intermittently. That means like On demand, we cannot ask for the renewable energy resource. For example, if you are considering the sun or something, if I wanted the sunlight or the energy during the night time, I cannot get it. Similarly, if you consider the wind energy, it is weather dependent, and depending on the day and time, the wind energy might be more, the blowing of the wind will be more, etc. Similarly, when you consider the geothermal or hydropower energy resources, they are specifically location dependent. So we have dams at specific places where you have a large water body, etc. And similarly, geothermal energy can only be extracted from a specific location. So as such, if you see renewable energy resources, although they are very good source of energy for us, they are either time dependent or weather dependent, etc., etc. What does that mean? When we want the power, we cannot simply ask for it and get for it. We need to first store the energy when it is there and reuse them when we want them. Okay, so for this reason, there are like various kinds of storage devices were invented. Like one of them is the rechargeable batteries. What are the other kinds of storage devices? You like this hydrothermal project also, hydroelectric projects which we might have seen, where you will be pumping this water uphill, and then you will use this gravitational force to just come this to be downhill, and you will be generating the electricity there. Or you can, if you heard of the flywheel, where you will be rotating some frame, rotating some rigid object, and you will increase its rotation, so you will be storing the rotational energy. There are various other kinds, like even fuel cells are there recently, and so on and so forth. So there are various kinds of ways you can store the energy that is generated using the renewable energy resources. For example, like sun energy, solar energy, wind energy, etc., etc. And once you store it, you can use it on demand. Okay, among these various kinds of storage devices, these rechargeable batteries are at the forefront, majorly because of their low cost and because they are highly portable. So among these rechargeable batteries, there are, like you might have heard of the lead acid batteries, sodium ion batteries, lithium ion batteries, nickel cadmium batteries, and so on and so forth. There are various kinds of rechargeable batteries are also available. Among them, right now, the top contestant we can say is like lithium ion batteries, and you have already seen like the mobile phones that we are using or the laptops that we are using, even the scooters, the electric vehicles, automobile industry is now moving majorly towards the lithium ion batteries. However, it is not the case that lithium ion batteries do not have any problems. First, we will see the working principle. So the simple working principle of the lithium ion battery as follows: like any other electrode material, it also has a cathode as well as an anode. Here, the cathode material is the lithium metal oxide. So it could be any kind of metal oxides here. So here, this is the lithium metal oxide, where during the charging, this is a most thermodynamically most stable state, and during the charging process of the battery, you will be pushing these lithium atoms, which are in the thermodynamically stable state, towards the anode material. Here, the anode material is represented as the graphite, which is a layered structure. So you are pushing the lithium atoms that are already in a stable state by applying some potential towards a higher way. So this is very similar to what we have told about the hydro energy project, like where you will be pumping the water that is available at a lower potential, that is on the ground, to a tank or something like that. So this is what we are dealing here. So you are pushing these lithium atoms, which are at a thermodynamically stable position, into the anode material. And since this is a not so stable one, when you stop the charging, the discharge will start, where the lithium atoms that are present in the graphite here, the anode material, will start to come back and come to the cathode. So while it is coming, so during the charging, the lithium ions are moving here and the electricity you are supplying. Whereas when during the discharge, the lithium ions are moving here, and you can use an external load like a screen or a bulb or fan or anything, where the electricity will be flowing through that and you will be using it. So this is the simple way to explain the working principle. And as I mentioned, the lithium ion batteries, although are at the forefront, they are not sufficient enough for the increasing demand. For example, when you are considering the electric vehicles, we want these electric vehicles to be having a long range nature. That means, like if you wanted to start from Madras and you wanted to go to Bangalore, you wanted to have one-time charging at your home and simply reach the Bangalore immediately, instead of charging at several times and several places. So for these kind of things, we are calling as the long-range electric vehicles, for which the current day batteries are not sufficient enough, and you need to find the alternative materials. So the current electric vehicle energy density demand should be more than 350 watt-hour per kg, and that is not the current one. There are various kinds of alternative battery technologies that have been proposed to improve this energy density. Some of the alternative technologies include the lithium sulfur or lithium air batteries. Apart from that, as I said earlier, there are different kinds of technologies, in the sense like you will not be using the lithium, but you can use the sodium ion battery, potassium ion battery, nickel cadmium, and so on and so forth. So apart from the long range vehicle problem, there is also an additional problem about the lithium ion batteries, that is the scarcity of the raw materials. If you are seeing the materials that are involved in the cathode, we said that it is like a lithium metal oxide. So what are the metals that are required? So this includes the nickel, cobalt, and even including the lithium. Lithium deposits are not similar to the petroleum deposits that are not distributed equally all over the globe. Similarly, the lithium deposits are also not distributed equally all over the globe. And the picture that we are seeing here is the top view from the Argentina, where you have a lot of lithium deposits are there. And the extraction of this lithium material from the minerals is a very consuming process, in the sense like you have to use a lot of water. And at these places, the South America and around the Argentina, there are like various places where there are drought prone areas, and if you are trying to extract more and more mineral from this manner, you are actually polluting the environment a lot, and you are like the surrounding ecology is like completely disturbed there. So not only that, even if you consider the materials like cobalt or nickel, cobalt is specifically there in the Congo, and as you can see, this is like more towards an illegal mining, and the human rights will be violated there. So in order to obtain the components that are there in the lithium ion battery, we are actually creating new kinds of trouble, and this will also slowly lead to the geopolitical tensions, because the lithium resources are not equally there, and the ways to abstract these ones are also not very good. As seen in this particular graph, the amount of lithium deposits, if you see, majority is there in the Chile, and some of them in the Argentina, Australia, etc. There is a recent one where they have said that lithium deposits we found in the Jammu and Kashmir. Despite that, what we want is some kind of resources that are equally available all over the globe, so that the interdependency will decrease. And because our energy demand is increasing day by day, everybody will be satisfied with their energy needs if the materials, the raw materials that we are using in these energy storage devices are available globally. So what are the other kinds of alternatives? There are various alternatives, as I told. Some of the cheapest alternatives would be to use materials that are similar to the lithium, but which are available everywhere. That is like sodium. There are also potassium, calcium ion batteries, magnesium ion batteries, etc. The important point that we need to understand is, for each of these battery technologies, the anode that we have used, for example, graphite is what we have used in the case of lithium-ion batteries. The same anode cannot be used. Most of the times, the same anode, same cathode, same electrolyte, these will not be working. So what we need to do is, we need to again find what is the best anode, what is the best cathode, what is the best electrolyte for each of these battery technologies, in order to get the best performance of a battery. Here, when we are saying about the best performance, it could be about the power density, charge density, and various other things. So all of these things should be there in our mind, and when we are preparing a new battery technology. So among these things, as I said, today's topic of our interest is only about the anode materials, and also those particular things that we can compute easily. Okay, this is what I'm going to tell you. So what are the good characteristics of an anode material? What are the characteristics of a good anode material? So the first one is, the material should be stable. When we are saying stable, it should be thermodynamically stable. It should be mechanically stable. Thermodynamic stability is very important for us. If it is not, because we will be repeatedly using these ones, it should be also mechanically stable, thermally stable, and dynamically stable. Dynamical in the sense like you will be what you say, using this lithium or any other particular material, any particular ion, you will be using again and again and again in the, because you will be charging and discharging and so on and so forth. So during this process also, it should be very much stable, and it should be a good electrical conductor, because you are considering that as an electrode material in the first place. Similarly, the material should have a high affinity towards the metal ion. For example, if you are considering it to be a lithium ion, and if you are assuming that to be a graphite as the anode material, this anode should be able to attract the lithium, and it should be able to hold that lithium atom first of all. If it is unable to hold the lithium atom, what will happen? These lithium atoms will start to interact with each other, and they can form an agglomerate, which is what we are calling as a dendrite. Once the dendrites are formed, they will be able to pierce through the separator, and they can create the short circuit. So for us, the first one of the important points is that whatever the metal atom is coming and trying to sit on the anode, that should have a higher affinity towards the anode, or the reverse way, the anode should have a higher affinity towards the metal atom. So this is one of the primary things. Second thing is the anodic voltage that we are going to generate should be as low as possible, because when you are considering the cell voltage is what we wanted to increase, and cell voltage is defined as the cathode voltage minus the anode voltage. So if the anode voltage is as low as possible, then the overall cell voltage will be better. So ideally somewhere around will be 0.1 to 1 volt. It's better if it is less than or 0.5 or so. So that's the where we are trying to see. So for the anodic voltage. Similarly, when you are during the discharge or the charging, as we said, we are trying to push the lithium atoms from the cathode material to the anode material, and there also these anode metal ions have to go and sit on various sites of the anode material. And when you are trying to discharge, all of these metal atoms that are on the anode surface has to come back. They all have to come back to the cathode surface. So they should be ready to have this fast charge or discharge kinetics, and for that you need to have a diffusion barrier for the metals, like for the diffusion from hopping from one place to the other side should be very low. Finally, after including or inserting these metal atoms, the interlayers between the expansion between these layers should be very less. Otherwise, if there is a huge changes in the volume, the batteries that we are using in the mobile phone, for example, you don't want your mobile phone to expand or contract just because you are charging, and that can also lead to other mechanical failures. So for that reason, you wanted the metal after the metal insertion or removal after the metal removal, the change in the volume should be as low as possible. And these are all together, when you are considering, these are the properties. First one is the thermodynamic stability, affinity towards the metal atom the anode material should have. It should have a low anodic voltage. It should be able to diffuse these metal atoms easily, and it should be very stable. So these are the properties that we will try to see how we can compute on the computer. So what I will do here is, like, I will consider the recently used material. This is called as anti-MXene material. This was recently discovered in 2021 by this group, Gu et al. And we will use this material. This is a 2D material. We will use this material as a prototype, and I will show how we calculated these properties. That way you will be able to understand. So many of you might have heard of the MXenes, these are like transition metal carbides or nitrates. So this is the metal atom, and this is the non-metal atom. Metal atom you can consider like this titanium or something like this. Okay, so this is the max phases they call this. So you can see here the green color is the titanium, the black color is the carbon, and in between there is an aluminum. So there is a metal, non-metal, metal, non-metal type layers are forming. So these are called as MXenes when you have a metal and a non-metal layer. Whereas when you have the reverse of that, that is non-metal will be there and below the metal will be there. That is what is called as the anti-MXenes. There were several anti-MXenes were found in this particular paper, and among these anti-MXenes, we just considered this cobalt containing anti-MXenes, because they found that cobalt boride has a very high specific charge capacity for the case of lithium. So we considered this cobalt containing anti-MXenes, and we studied each one of these properties that I have mentioned to you earlier. So this is how they look like, the cobalt, arsenide, boride, phosphide, and so on and so forth. And as I mentioned, this is the metal atom. Above and below you have the non-metal atoms. Now what we are trying to understand is whether if we form a 2D layer of this one, this is actually a 2D layer, just I have shown you the unit cell. This 2D layer is there with you as an anode material, and if you form multiple of these layers, and if you start putting these metal atoms on them, how they will be reacting, and what kind of specific capacity that can give, what kind of voltage it can give, etc., etc. This is our understanding. So first we have studied the dynamical stability of these systems. So here basically what you need to understand is, like, whenever there are no negative frequencies in them, they are called dynamically stable. As you can see, there is no such negative frequency here. So all of them can be considered as a dynamically stable materials. And how these materials are stabilized is the question. If we ask, we have plotted what are known as the electron localization functions, as you can clearly see from these ones. So this is the metal atom and this is the non-metal atom, and you can see that the electron cloud is majorly localized on the non-metal atoms. That means this is like a ionic type interaction which is stabilizing these systems. Metals, there is no such electron cloud is not there. So that means electrons are completely localized on the this non-metal atoms. So you can see like anion cation type of interaction, which is nothing but the ionic type of interaction, which is stabilizing these materials. Next, first among the important points, these anodes should be good conductors of electricity. For that, we have plotted the electronic structure, that is the band structure and the density of states. If you see this band structure, in general, when you see the band structure, if there are energy levels at the Fermi level, so this is the Fermi level, this dashed line, horizontal dashed line. If you see here, the bands are crossing at the Fermi level, which automatically suggests that this is a metal. Okay, so similar kind of things you can see for other cases also. In all these cases, you can clearly see that the bands are crossing, and see the same kind of information you can also get from the density of states. You should see the density of states by rotating your head here. So if there are finite amount of density of states at the Fermi level, that's what is called as a metal. If there is a gap, that is called as a semiconductor. If the gap is very huge, that's what you call as an insulator. Clearly from these figures, you can understand that all the cobalt anti-MXenes are good electrical conductors because they have the finite density of states as well as the bands are crossing at the Fermi level. So after we understand that these are good electrical conductors, next thing that we need to understand is how tightly this material is able to bind this metal atoms. So here we have considered all the 6 different kinds of cobalt anti-MXenes, and for each of these ones we have calculated the absorption energy of lithium, sodium and potassium. So these are separate calculations, and once you are considering this surface, the surface will have many sites to get for this metal atom to be absorbed. So we have considered like this 6 metal atom absorbing sites. So these are the symmetric sites these are the different kinds of sites that are possible on this anti-MXene. Here whatever we are showing is for the cobalt sulfide, but the similar kind of picture will come for all the other materials. And similarly here we are showing for the sodium atom. Similarly for the case of lithium and potassium also, you will be seeing all these positions. So once we consider this material and we kept each one of these atoms at these places and we measured what is the absorption energy of this, and once after measuring we found that some of these sites like S4, S5 and S6, they are not very stable, and once you put an atom at that S4, S3 or S5, S6 sites, they will simply move to either one of these S1, S2 and S3 sites. Okay, so for that reason we have only provided the results of the S3, S1 and S2. So among these 3 sites, S3, S1 and S2, the site S3 is the most stable one. That means if you are assuming that material is there and if you just push a lot of lithium atoms, majority of the times you can be expecting that they will be absorbing onto this S3 site. So among the different kinds of metal atoms, if you see, these cobalt anti-MXenes have a higher bonding energy towards the potassium when compared to the sodium and the lithium. So this is the absorption energy order across the materials, and also when you are considering a specific metal atom, potassium is the one that is strongly absorbing, and when you are seeing the sites, it is always at the S3 site. So next question is why it is absorbing strongly at the S3 site, why not at the S1 and S2 sites? So for that we have plotted what is known as the charge density difference. For this what we do is you consider the total system, that is the anode surface plus the metal atom. You calculate its total charge density and you subtract this charge density from the individual ones, that is the separate 2D layer and also the separate metal atom. If you do this, what you will be able to observe, from where the electron density is removed and from to where the electron density has gone, that will give us a picture of what kind of rearrangement in the electron density is happening, and that can further give us an understanding. So these are the plots that we got it from S3 site, S1 site and S2 site. These are the charge density difference plots. So you can clearly say for all the 3 cases, this is the charge accumulation. That means between the metal atom and the non-metal site, there is an accumulation of charge at the S3 site, whereas the charge depletion is happening from the metal. That means there is a transfer of the electrons from the metal site to in between the metal and the non-metal sites. That means there is a strong bonding that is forming between these two. And at the S3 site, as you can clearly see, there are 4 such strong bonds are formed, whereas at the S1 there are only 2, and at S2 there is only 1 bond. Accordingly, we can clearly see that S3 site should be the most stable site, and that is exactly what we have observed. After that should be S1 and after that should be S2, because S1 has 2 such anchoring points, whereas S2 has only 1 anchoring point. And as you can clearly see, that's what is happening, and even the results are suggesting the same. So once we understood that, these materials can absorb these systems strongly. Also, you can see the energy values. These are more or less in the chemisoption type values, like minus 1.3 electron volt, or somewhere between 0.7 to minus 1.3, or even something little more also are there. So as a whole, they are strongly absorbing, which means, as I mentioned earlier, these metal atoms, after absorbing onto the anti-MXene materials, they will not come and form a dendrite. That is a good thing for us. So these are, in that way, these are a good anode material is what we can tell. They are good electrical conductors. From the absorption energy values, you can also say that they do not form the dendrite, so we can proceed further. So what are the other properties we need to further check? Next thing is, as we said, we need to understand whether the diffusion kinetics will be easier or not. So for this, we need to calculate the migration energy barriers. So we have used what is known as the climbing image nudged elastic band theory in order to calculate this diffusion or the migration energy barriers. For this, again, on the material, there could be several paths. In a metal atom can move from one side to the other. So accordingly, we have considered three paths here, three different kinds of paths. Among these three paths, the path 2 was again not stable. Whenever we are trying to optimize the system along the path 2, it is falling back to the path 1. So essentially, we got path 1 and path 3, and what we found was path 1, which is given by the stars here, is always the low energy path. That means it metal atom should prefer to go along this direction when compared to the path 1. Again, obvious question is why path 1 is more stable when compared to the path 3. The simple explanation is based on the earlier charge density differences. We have seen that S3 site is the most stable site, but after the S3, the next stable site is S1. So when you are trying to move along this path 1, what you are finding is you are on a very stable site, and you are simply moving to the next least stable site, to the S3 site again. Whereas here it is not so stable. So in reality, what it is happening is you have to climb the ladder very high in order to come back to the site. So that's the reason there is a high migration energy barrier when you are trying to move along this path rather than along this path, which is the path 1. Okay. So once we understand that, we calculated the diffusion energy barrier for all these materials as well as for the lithium, sodium, and potassium. And as you can see here, the diffusion barriers for the potassium are the lowest along the path 1. Okay, so we are no more calculating path 1 and path 3 because we already understood that path 1 is the most stable one. For the path 1, for all these systems, arsenide, cobalt, arsenide, boride, etc., for lithium, sodium, potassium, when you are comparing, what we are observing is potassium is the one that is having the least barrier. Again, obviously, this is an important question to ask, why potassium is having the least barrier. So two ways we can understand it. So the obvious point, as I told you earlier, among the three, lithium, sodium, and potassium, potassium is the one that is having the strongest absorption. If you see here, let us compare for the cobalt arsenide. Lithium is absorbing with a minus 1.3, sodium is with minus 1.2. Both of them are roughly the same, whereas potassium is absorbed with an energy of minus 1.7. Similarly, you consider for any other material. Let us consider cobalt sulfide, 0.95, 0.96, roughly the same, whereas this is absorbing with minus 1.5 energy. So as such, potassium is the one that is absorbed very strongly onto this material. But what we are finding here, the migration energy barrier for the potassium is very less. So for some people, at least, this is very counterintuitive, because your potassium atom is very strongly absorbing onto this material. Why for that the migration energy barrier is very less? Okay. So the reason for this is, like, the picture that we always have is, when something is strongly bound, we cannot move it. Okay, this is slightly a wrong picture. When we are saying about the absorption energy, it is essentially how much amount of energy you need or you obtained after absorbing. Another way to see is, like, if you want to remove this atom completely away from the surface, how much amount of energy you need. Whereas for the migration, it is, you do not need all that energy to remove this atom completely. What you need is to move from one side to the next side, or even intermediate sites also. So accordingly, since the difference between the energies of two sites, like let us consider S3 site and S1 site, if the difference between the S3 site and S1 site is less, then the amount of energy required to migrate on the surface will be less. So we have plotted those kind of differences in the sites, and you can also see from these values as well, if you wanted to compare the differences. but I don't want to go into that much details. Just you take my word here. So what we observed was, for the case of potassium, the difference between the S3 and S1 sites or S3 and S2 sites is smaller. For that reason, the diffusion energy barrier for the potassium is lower when compared to sodium and lithium. So this is what is the picture that you should have. You are not supposed to remove the complete atom like this and then again throwing it in the next pocket. Rather, this is like a continuous migration. So it is moving from this one of the stable S3 sites to another S3 site in this particular direction. And for each of these ones, these are like your baby steps. You are not trying to climb the wall at a time. Rather, you are taking the steps to climb up and coming down. So that's the reason for the case of potassium, it is a smooth one and the amount of energy required is very less. Okay. So now we understood that among these various anti-MXene surfaces, lithium, sodium and potassium are there. Potassium is able to easily diffuse on the surface, but lithium and sodium are also reasonably okay. They have only 0.6 or 0.8 electron volt migration energy barrier, and all of them are absorbing strongly. All of them are good electronic conductors. So till here, whatever we have discussed is with one metal atom on the surface. Now, when we are considering the real battery, as you know, when you are, for example, charging or discharging, a lot of metal atoms will be involved. So this is what we are trying to understand next. So how many number of metal atoms this particular material can actually absorb? We said only, we worried till now only about for the one particular metal atom. So if you consider the multi-layer absorption is also thermodynamically feasible sometimes. So here I have just given you the values. So don't worry by the lot of numbers that are there here. Essentially what we wanted to see is, if you wanted to load multiple number of metal atoms on the surface, till where this this surface can hold the metal atom. So for example, if I'm considering graphite as the material or graphene is the material here, if I'm adding first lithium atom, whether it is able to absorb with the negative energy or not, second atom again whether it is able to absorb with the negative energy or not, and so on and so forth is what I'm checking here. So like that, when I checked, as you can see, the bolded ones are the ones that corresponds to the negative energies. So for if I'm considering cobalt arsenide for the lithium, I can immediately see that for the first lithium atom absorption it is fine, for the second one it is not. So it is giving positive. That means cobalt arsenide can only have one layer of lithium atoms. So here I am saying layer because I considered a 1x1 unit cell. That means only one small portion is considered. So it will be repeated all over the place. That's the reason I am calling it as a layer. So for the case of cobalt arsenide, only one layer of lithium can be absorbed, whereas I found that it can absorb up to 3 layers for the sodium, whereas for the potassium it is only again 1 layer. So you might worry that, oh, this is also negative, why he did not consider. Okay, so the reason is there are several places where we should not be considering. For example, when you are trying to increase the number of metal atoms, you obviously know that like the first layer, if it is absorbing strongly, second layer the absorption energy should decrease. You cannot continuously have more and more and more. If you are seeing that there is a more negative absorption energy after the third layer to fourth layer, that essentially means that there is some agglomeration is happening. There are some bonds between the sodium atoms. For this reason, we will not be considering such scenarios. So essentially, like this, we have calculated for all the systems, and we have found that certain systems like cobalt phosphide can load up to 5 layers of lithium. That means it can take a lot of lithium atoms onto it. Okay. So there are various cases where we did not consider the absorption. So first case, as I said, was if the first layer, L minus 1th layer is negative, L plus 1th layer is positive. Sorry, Lth layer is positive. Anyway, we will be discarding that. Second thing is, Lth layer is more negative than the L minus 1th layer. For example, as I said, third layer is more, fourth layer is more stable when compared to the third layer. Again, you have to discard such kind of things. And a few cases, absorption energy will not change as you are increasing the layer by layer. Again, this is also not physically feasible because you are adding more and more atoms, but absorption energy is exactly the same. So that is not feasible. So we will discard all those kinds of scenarios. If you discard all those kinds of scenarios, what we found was for the case of this lithium, I will just show you the values once and I will come back to this. So you can find that for certain cases, like for the case of lithium, it is the cobalt silicon and cobalt phosphorus that are absorbing the most. Whereas for other systems, it is similarly for the sodium, it is also cobalt Si. Sorry, not cobalt Si. Apart from the cobalt Si, everything else is able to absorb up to 4 to 3 layers. You can see here, like up to 3 layers, it is okay. Whereas for the case of for the case of potassium, they are unable to absorb more than 1 layer. So for the bigger picture is lithium, sodium, potassium. Potassium is only able to absorb 1 layer. Sodium can absorb up to 3 to 4 layers, whereas lithium can be absorbed more on these cobalt surfaces. Only certain ones will be there that they will be able to absorb more, like the cobalt phosphide for the case of lithium. Okay, this is the one that we have calculated. Next thing that we need to find is like how do we calculate this average voltage. Okay, so if you see the simple reaction, you know that metal is going to give rise to metal, that ion plus the electron, and here the cobalt anti-MXene is the one that is taking the electron, and if you just add these two equations, what you are going to get is the potential metal insertion voltage. This is the metal insertion voltage equation, and we know that we want the anode voltage to be less. If the anode voltage to be close to 0, that means how much amount of energy that you need to add the electron. This particular reaction and this particular reaction should be roughly the same. So the electrochemical behavior of the anode material that we are considering should be similar to that of the metal anode. If you are considering the lithium ion battery, it should be similar to the lithium ion anode. If it is you are considering sodium, it should be sodium anode. Okay, that's all. So how do we calculate the metal insertion voltage? So metal insertion voltage can be easily calculated by calculating the adsorption energy, and that's the reason we have calculated this adsorption energy. Why it is the case? So from the second law of thermodynamics, you know that delta G can be calculated in this way. For the case of these adsorptions, generally the P delta V term and the T delta S term can be very low. I have just given here the example for the P delta V. For example, you know that at the standard conditions, P will be about approximately 10 to the power of 5. And if you are assuming the cell volume, that can be maximum of 100, 10 cross 10 will be the volume generally. So that's the reason I'm considering 100 angstrom cube. So if you are considering 100 angstrom cube, now you calculate what is the 1 electron per angstrom cube. 1 electron per angstrom cube, after you rewrite everything, it is coming to be 0.624 into 10 to the power of minus 6. And if you multiply, this is the pressure, you multiply this pressure with the delta V, which is about 100. If you multiply, the overall energy you are getting is in the order of 10 to the power of minus 5 eV. The absorption energy delta ES that we have seen earlier is minus 1.3, minus 1.5, even minus 2 is there. So when 2 electron volts versus 10 to the power of minus 5. So we are comparing with 1 rupee versus 10,000 rupees. So that's the difference, or the opposite way. Okay. So that's the reason we are completely neglecting this P delta V term. Similarly, we can also neglect the T delta S term. So accordingly, the delta G value for this reaction is essentially, or the voltage is metal insertion voltage, can be written as minus delta E adsorption energy per Faraday constant. So this is how we have calculated these ones, and we have plotted and we obtained. So the metal insertion voltages were about 0.3, 0.4 at around that average ones. If you are calculating the average of these values, that's the range that we got. Accordingly, these are good, they have good voltages. Okay, anodic voltages are very good for these materials. So next, after calculating this, we also wanted to calculate the specific charge capacity, which is telling us about how much amount of the charge per gram you can store on these materials. As the the formula for calculating this is this, where n is the number of alkali metal atoms adsorbed onto the formula unit. So if you remember, for the case of lithium, cobalt phosphide is the one that adsorbed about 5 lithium layers. For that reason, you can see the specific capacity for that is very high, because for the specific charge capacity is directly proportional to the number of atoms. The charge is same for all these lithium, sodium and potassium, because it is only going to deliver 1 electron. The only difference will be based on the molecular weight. Since potassium, if the number of atoms or number of layers adsorbed on a system are same. If you remember again, cobalt arsenide, I told that lithium will be only absorbing 1. So, and also for potassium, all of them are only 1. So when the system is having high molecular weight, so lithium obviously is lower in molecular weight than potassium. So you can see that lithium has a high specific capacity when compared to the potassium. Similarly, if you see boron, because cobalt boride is there and cobalt arsenide is there, since boron is having a lower molecular weight compared to the arsenic, so when although potassium is only 1 layer of potassium is adsorbing on both the cobalt arsenide and cobalt boride, the specific capacity is more here because this is in the denominator. So like this, you can calculate for the specific charge capacity, and the specific charge capacities are very high, is what we have observed. At least like all of them have about, I mean, for the case of sodium, you can see clearly that majority of them are having 400 or so, 400 milliampere hour per gram or so, and some of the lithium ones have shooted up to 1000. So these are very good values for the case of specific charges, specific charge capacities. So as a whole, till now, whatever we have considered, these are very good electrode materials is what we found, because they are metals, they are absorbing strongly, even multiple layer absorption is okay, diffusion barriers are okay, voltage profile when you are seeing, that is also okay, and even the specific charge capacity is okay. So what are the other things that we need to check? The other thing is the thermal stability. What we can do is, like, you can consider the highest adsorbed. That means, like, if when you loaded the maximum number of layers. So here, for example, if you consider this is the COP, for this you have loaded up to 5 layers. You take this 5 layer COP and then you run the molecular dynamic simulation. So at a specific temperature, here we ran it for the 300 Kelvin because we just wanted to understand at room temperature how does this behave. As you can clearly see, this is the initial optimized structure, and after running for 15 picosecond simulation, you can see that there are only very slight structural differences. This is suggesting that at 300 Kelvin, this particular 5 layers are thermally stable. And also you can see the energy differences. If there are any bond formations or something, there will be a huge energy fluctuations will be there. And you are not seeing such things, suggesting that this is a good, they have good thermal stability. Similar kind of calculations we also ran for the sodium on cobalt sulfide. So that also gave roughly the similar results. Next, why the question that we asked was why these lithium ions or potassium, sodium ions were able to absorb more, whereas the potassium, so lithium and sodium are able to absorb more and potassium is not absorbing more. So by plotting the ELF plot, that electron localization functions which I told earlier, what we were able to see is there is some electron cloud. If you see the scale here, if there is green or orange or red, that means there is some electron cloud is there in between. So between these ions, there is some electron cloud to stabilize on the cases of lithium and sodium. Whereas if you are considering the potassium, there is no electron cloud between these two, suggesting that they are able to have a very strong interaction or strong repulsion, which is avoiding for it to absorb further. Okay, this is the major reason for potassium being able to absorb only till one layer, and this is what is our interpretation at least. Okay, so finally we have also considered the how much there is enhancement, how much, like, whether the layers and layers are expanding or not. Even for the case of 5 layers we have considered. So one layer you can clearly see that there is not much change. For 5 layers, although you might feel that this is a lot of increment is there, and if we compare it with the already well-known structures, the increment in the interlayer spacing is pretty minimal. Okay, so based on these results, we confirmed that these systems have very good stability. Also, the interlayer spacing and other things also will be very minimally affected. So, considering all of these things, we can conclude that the newly developed cobalt anti-MXenes are electrical conductors and they are definitely dynamically stable. They have high chemisorption, or like at least moderate to high chemisorption for the alkali atoms. That means they are not going to form any dendrites, and they have low diffusion energy barriers, so they can easily go during the charging and discharging on these surfaces. Similarly, because of this high specific charge capacity, they might have good usage in the energy storage materials. Similarly, maximally lithiated and sodiated structures, we check their high thermal stability as well as the electronic stability. The negligible interlayer expansion after lithiation and sodiation suggests that the deformation after many charge and discharge cycles will be very less. So, considering all of this, we can suggest, okay, cobalt phosphide is good for the lithium and cobalt sulfide for sodium, etc., etc. So that's the major message I wanted to give you. So as a whole, what we have shown till now is you can calculate some of the properties that are useful or related to the anode materials and whether they are going to be useful or not. The properties that you need to calculate are very simple. These are directly available in any DFT package. We have used vast DFT package in order to calculate this, but you can also do the same thing using quantum espresso or any of the other periodic systems. So what are the properties that you need to calculate? If you remember, first one is you first need to calculate whether it is a metallic system or not. For that, all you need to do is band structure and density of states. Next, you need to calculate its adsorption energy. If the adsorption energy is reasonable, you are confident that it will not form the dendrite. And then you need to calculate the diffusion energy barrier. If the diffusion energy barrier is lower, that means it can easily move on the surface. And how do you calculate the diffusion energy barrier? You will use what is known as the climbing image nudged elastic band. And in order to understand the adsorption, why there is a stronger adsorption, etc., There are also population analysis, which I did not show you here, but we perform. But what I have shown you is the charge density differences is what we have used in order to explain the higher stability of at a particular site when compared to the other sites. If you remember, S3 site was the most stable site, and at the S3 site, the charge densities between the lithium atom or any metal atom and the non-metal atoms are more. After that, you need to calculate whether multiple layers of these metal atoms can be absorbed or not. If they are able to absorb, if you are able to get a large specific capacity value, that is very good. And if the average anodic voltage is less, that is also very good. And then you need to also ensure that there is a high thermal stability. So you need to construct the system and you need to run a molecular dynamics run, MDT run or something of that kind at 300. Even you can also try to run it at 500 Kelvin, because sometimes we heat up the batteries while charging and discharging. So you can little bit consider that place and you see whether they are agglomerating or not. If they are agglomerating, that means that these are not good materials, because they can form again dendrites and they can create some problems. If not, that is a good thing. Similarly, other properties like whether the expansion is more or not, you need to check. If the expansion is reasonably okay, you don't need to worry about this. So these are the properties that you can check for any other anode material. And I stop here. I would like to just thank Subhadeep, who is one of the main persons who worked on this one. Apart from him, there are also other students who worked on this kind of projects. One person is Ankita, another person is Kalpak from my group. And I would like to thank IIT Madras, SERB, for the funding, and of course IIT Madras for giving me this position to deliver you a talk. Thank you all for your patience. I am open to questions.
Thank you, Dr. Chaitanya, for an excellent informative talk. You really explained clearly the various computing steps which are involved in arriving at a very promising anode material for battery applications. I really thank you for sharing your recent research in this area. Now, this talk is open for questions. Questions, please. You can just unmute and you can ask the questions.
Dr. Chaitanya?
Yeah.
Yeah, it's an excellent talk actually. Just what I wanted to, I'm Parvatalu, I'm moving this connection. Just I wanted to ask you that any validation of this kind of data is done, actually any effort has been done by anybody else, or you have some kind of plans to get it done? Because this is an excellent work, that's a different thing, but ultimately real applications, they need some kind of validation.
Agreed, sir. So, but we did not approach yet. This is like our for our student. We wanted to train on this. How do you calculate for the different anode materials? That is the reason we have done this work. But definitely, as you said, like if we can validate these kind of systems with experiments, that would be wonderful. But we did not do, unfortunately, for this particular case. These are theoretically predicted materials. They have to be synthesized experimentally. Only one of the anti-MXenes was synthesized till now, which is iron selenide, if I remember. FeSe is the one that was synthesized. So other materials have to be synthesized first before trying for these ones. But we are definitely interested in exploring similar kind of things for the materials that are already available, and that work is under progress. And Subhadeep is working on a few other materials for which experiments can actually validate our results.
Thank you. Another thing is that you need some kind of your preliminary screening of these materials when you are choosing such kind of materials. Okay, one part is that their electrochemical characteristics and basic information that is required for getting into electrode material, anode material, and all. But then you look into the safety aspects of this kind of materials while screening these materials.
Safety as such, sir, like we are only seeing whether as I explained, only a few chemical properties, but safety, how do we say, like whether they are thermally stable or not.
Yeah.
These are the kinds of things we are looking for, but we cannot, I mean, computationally we cannot burn a chemical and see there. So that's
no, I'm not asking about your computations actually. While screening, before screening such kind of materials and before going into research, actually, that's the reason I'm telling that you have some kind of criteria that the following things are needed before going for such kind of studies, so that at least see, one is that you can compute certain kinds of things, and then based on which you will be arriving the materials, and when the materials are tested, and then when you find the abnormalities, then you will be discarding or you may be modifying. That is a different thing. But if you have some kind of database already available with you, then I can screen and then go for it. So that is the gist I'm asking about these things.
Okay, okay, sir. I understood. Okay, I need to think about this, sir. What are the criteria on which you can actually screen? So obviously, like maybe thermodynamic stability, these are there, but I should think, sir. I don't have an idea directly to tell you, but I should think about this.
Thank you.
Yeah, thank
you.
Yeah, but that is a nice point. Like there are existing databases definitely. So if you wanted to screen, what are the criteria that you will keep to screen this is your question. I understand that, but I'm not able to answer immediately. What are the criteria that we can keep? Definitely, like metal and these kind of things, we can always do. But beyond that, what we need to do is something that is interesting. There is a recent one package I forgot. If Subhadeep is there, you can tell Subhadeep that name of the package that we recently encountered in that electrochemical symposium only. So where you can screen a lot of materials like based on certain criteria which they have mentioned. This is from Singapore, one person, I forgot the name, Simons or somebody. So if you are there,
Stephen Adams.
Stephen. So what is the package name, Subhadeep?
That is.
Okay. Fine. If you find, just put it in the chat box. Yeah.
Sure, I will put
Yeah.
it.
Thank you.
Any more questions?
Thank you.
Thank you, Professor.
Dr. Chaitanya, I just have a question.
Please,
do you take any like the thickness or something in your calculation part? Do you consider the thickness of these layers?
No, madam. We have only considered one layer and we have done. But
Okay.
for other battery, like we are trying already for the borophene material. There we are trying to vary number of layers and we are trying to understand.
Okay.
Yeah.
What is the thickness of each layer now? Whatever you are
This is
referring.
atomic thick, madam. So just
Atomic. Okay. 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 Any more questions? Okay, I think there are no more questions. Please join me in thanking Dr. Chaitanya for an excellent and informative talk.
thank you.
Thank you, Dr. Chaitanya.
Thank you.
Thank you so much. Thank you. And I thank you all for joining and making this event a success. Thank you all.
Thank you, madam. Thank you,
Thank you, sir.
Chaitanya.
Thank you, sir.
Thank you very much.